In this video, we will be discussing about the stability analysis of discrete time systems. Stability analysis of discrete time systems. So a discrete time system can be represented either as a difference equation or a transfer function. So we have seen the difference equation representation, the transfer function representation, and so on. So here the discrete time system is represented with the help of transfer function. For example, let's say h of z be the transfer function of the discrete time system for which we need to do the stability analysis. This h of z is given by y of z divided by x of z. So this y of z is the z transform of the output and x of z is the z transform of input. So this h of z gives the transfer function of the system, which is the z transform of the impulse response. Now, if you are provided with the transfer function of a system, how to check whether that system is stable or unstable? So we are talking about absolute stability and not about the relative stability. Now, if you remember the mapping of S-plane to Z-plane, so we have seen that the mapping is given by Z equal to e raised to S capital T. So capital T is the sampling period, S is the Laplace variable, and Z is the Z variable. So by this mapping, we have seen that the imaginary axis in the S-plane is being mapped into the unit circle in the Z-plane. Suppose this is S-plane, and on the right side I have drawn the Z-plane. And by this mapping, we have seen that the imaginary axis is being mapped to unit circle in the Z-plane. So if you remember, the condition for stability in the continuous time system or in S-plane is that we require the poles of the transfer function. So suppose h of s is the transfer function of the continuous time system, which is equal to y of s divided by x of s. And suppose we find the poles of this transfer function, and we require the poles to be on the left hand side of the S-plane, left hand side of the imaginary axis, and we require all poles to be on the left hand side of imaginary axis for the continuous time system to be stable. So if there is a pole on the imaginary axis, it need to be a simple pole for the system to be stable. So if there are multiple poles in the imaginary axis, then that system is unstable. So if there is a complex conjugate pair, that is also a stable system. If there is a multiple complex conjugate pole at the imaginary axis, then that is also unstable. So by mapping this into the Z-plane, the condition becomes the poles of the Z transfer function need to be inside the unit circle. So if it is a complex conjugate pole, it need to be inside the unit circle. And if there is a simple pole at the unit circle, that is marginally stable, but that is still stable. And if there is a complex conjugate pair pole at the unit circle, that is also marginally stable. But if there is a multiple pair of poles like this, so here I have a complex conjugate pair as well as a simple pole at the unit circle, then this condition is an unstable condition. So there can be only a maximum one simple pole or one pair of complex conjugate pole in the unit circle for the system to be stable. If there is any pole which is outside the unit circle in Z plane, then that system is a unstable system. So depending upon the pole location, the stability can be determined. If all the poles in the Z plane are inside the unit circle, then we can straight away say that the system is stable. And if there is a pole in the unit circle and the remaining poles are inside, then that is also stable. If there is a complex conjugate pair at the imaginary axis and the remaining poles are inside the unit circle, then also the system is stable. If there is at least one pole which is outside the unit circle, then the system is unstable. So the poles of the characteristic, the poles of transfer function, the poles of h of z gives the condition on stability. So the poles of h of z is actually given by the roots of characteristic equation. The poles of h of z is given by roots of characteristic equation. Characteristic equation. So what is this characteristic equation? So let me denote it by P of z. So this characteristic equation is actually the denominator polynomial in the transfer function, which is equated to 0. So P of z is equal to 0. So I'll repeat it once again. So this is very important. Characteristic equation, CE, characteristic equation is the polynomial, the denominator polynomial of the transfer function. So this transfer function is a fraction. So the denominator polynomial equated to 0 is the characteristic equation, and the roots of this equation, the characteristic equation, is the poles of the transfer function. And if the poles, the magnitude of the poles are less than 1, if all the magnitudes are less than 1, then that is stable. If there is any pole which has magnitude greater than 1, then that is unstable. Now a quick word about the closed loop system. So here I have talked in general about the open loop system. So now what is the characteristic equation? What is the characteristic equation of closed loop system? So sometime in question you may be directly given with the characteristic equation of closed loop system. Then you can work with the characteristic equation directly. In some other cases you may be provided with the transfer function of open loop system, and you need to find the characteristic equation of closed loop system. So a closed loop system is represented by, for example, g of z is the transfer function of the open loop system, and suppose you are asked to find the characteristic equation, or you need to check the stability of unity feedback control system or something like that. So if you have a system something like this, so let's consider the controller as unity, and the feedback or the sensor is also unity feedback. So let's consider a simple system something like this. So here I have plus, minus, here I am giving the reference input denoted by R of Z. Here I have the output which is denoted by Y of Z. So the transfer function of the overall system, which is given by Y of Z divided by R of Z. Y of Z divided by R of Z, which is equal to, in this case it is 1 divided by 1 plus G of Z. Okay, so if there was, so I'll add that as well, if there was a sensor or a feedback dynamics which is given by maybe H of Z, then it would have been 1 so it is actually a G of Z by G by 1 plus G H Z. Okay, so what I was talking about is what is the characteristic equation. That's what the focus all about. Okay, so the characteristic equation for a closed loop system is actually, it becomes 1 plus G of Z, H of Z. If H of Z is 1, if it is unity feedback, then it is 1 plus G of Z equal to 0. So I just want to mention this quickly. So if there is a gain k, for example, so suppose in some questions you will be asked to find the gain k to make sure that the closed loop system is stable. So in that case, this characteristic equation become 1 plus k into g of z. Okay, so in that case you have 1 plus k into g of z equal to 0. Yeah, so this is the characteristic equation of the closed loop system. Okay, now coming to the methods for to check the stability of discrete time system if you are given with the characteristic equation. Okay, so now we are given with the characteristic equation. So let me denote the characteristic equation by p of z equal to 0. What are the different methods? So method 1 is a pretty straightforward method. Is you try to solve this equation or find roots of p of z. Find roots of p of z equal to 0. And what is the stability condition? Stability condition says that if the magnitude of all the roots is less than 1 for all I, then the system is stable. Then system is stable. And if there is only one pole at z equal to 1, then also the system remains stable. And if there is any pole which is having the value greater than 1, if any, then system is unstable. Okay, so this is the basic condition that we were talking about. But the issue is that it may not be easy to find the roots for big polynomials. Okay, so our calculator may not be able to solve for degrees greater than or equal to 4. So up till 3, maybe you can just find the root of the characteristic equation to check whether the system is stable or not. And there are two more methods which is very popular. The second method is called as Jury's stability test. Method 2 is Jury's stability test, which we will see in a moment. And the third method is by using something called as bilinear transformation. Bilinear transformation and Routh's stability condition. So this Routh stability condition is the stability condition or stability criteria that we use for continuous time system. So what we'll do in bilinear transformation is we'll transform from Z domain to a new domain called W domain, which is similar to the S domain, and there we will use the Routh stability criterion to check the stability. So now we will focus on these two methods, the Jury stability test and bilinear transformation with Routh stability criterion. Now talking about the Jury's stability test. Jury's stability test. Remember that we are provided with the characteristic equation P of Z. So assume that the characteristic equation is given by P of Z equal to A0 Z raised to n, A0 Z raised to n plus A1 Z raised to n minus 1 plus a2 z raised to n minus 2 plus etc. up to the second last term being a n minus 1 z plus an. Okay, so this is the characteristic equation, and this is equated to 0. So this is an nth order polynomial, and we require this a0 to be a positive value. So if it is not positive, you can if it is negative, you can multiply it by throughout by -1 to make it positive. So this a0 need to be positive. Okay, so the jury's stability condition, so we need to construct something called as jury's table. We will come into that. So so the condition, I'll write the condition and then I'll come into jury's table. So the condition is that the system with characteristic equation P of Z, so the system is stable. So I'm talking about the condition for stability. The system is stable if there are 4 conditions, and if these 4 conditions are satisfied, so I'll write 1, 2, 3 and 4. So if these 4 conditions are satisfied, then you can say that the system is stable. If any of these conditions are violated, then the system is unstable. So the first condition says that we require the magnitude of an, the constant term. So this magnitude of an must be less than a0, the first term, coefficient of z raised to n. So that is the first condition. Second condition is we need to check p of z for z equal to 1. And if this need to be, this p of z at z equal to 1 need to be greater than 0. It need to be a positive value. So that is second condition. Third condition is p of z at z equal to -1. So this you need to check, z equal to -1, and it has 2 cases. It need to be greater than 0 if n is even. If the order is even, then it need to be greater than 0, and it will be less than 0 for n order. Third condition. And fourth condition, I'll just write down now, and this is coming from the jury's table. So we require b of n minus 1, magnitude of b of n minus 1 need to be greater than magnitude of b0, c of n minus 2 greater than c0, and so on. Okay, so these are coming from jury's table. Okay, so if a system satisfies these 4 conditions, then we can say that the system is stable. Now, yeah, so how to construct a jury's table and how to get this b of bn minus 1, p0, cn minus 2, c0, and so on. Okay, so so in order to construct a jury's table, what you need to do is so now I am talking about jury's table. So it's very easy. There is nothing much difficult in this. So here you need to write rows. So row 1, 2, 3, 4, and so on. And at the top you need to write z raised to 0, z raised to 1, z raised to 2, z raised to 3, etc. up to z raised to n. Okay, so on the column you have z raised to 0, etc. up to z raised to n, and here you have the rows. So you need to fill 2 rows at a time, something like this. So 1 and 2 row need to be filled together, 3 and 4 rows need to be filled together, 5 and 6 need to be filled together, something like this. Okay. Now it's very easy. You need to fill the coefficients of z raised to 0. So if you see, the coefficient of z raised to 0 is an. Coefficient of z raised to 1 is an minus 1. Okay. So here you have an, this is an minus 1, next is an minus 2, and etc. And this goes up to coefficient of z raised to n is a0. So this forms the first row. Second row is just the reverse direction. So it is a0, a1, a2, etc. The second last element being an minus 1, the last element being an. Okay, so this is the first and second row. Now the only thing is how to fill the third row. Okay, so please listen carefully. In order to get the element here, which is actually b of, so here it is a of n, so here in the third row we have b of n minus 1. Okay, so in order to get b of n minus 1, you need to take the determinant of this row along with the last row. Okay, so the determinant of this, so I'll write here b of n minus 1, b n minus 1 is actually determinant of an, a0, a0, an. Okay, so this is bn minus 1. So what will be a bn minus 2? So in order to get bn minus 2, it is actually the determinant of the just previous element. Okay, so this is a1, determinant of the first column, this column, along with this column elements. Okay, so I'll write here bn minus 2. So this is bn minus 2. bn minus 2 is actually the determinant of an, a0, a1, an minus 1. So this first column and the second last column. So it forms bn minus 2. Similarly, it continues bn minus 3, and it continues till the last element, which is b0. So this is the only thing that you need to understand in this construction of Jury's table. So bn minus 1 is first column and the last column. bn minus 2 is first and the second last, and so on. Once you have this, you need to just write it in the reverse order. So it becomes b0, b1, b2, etc. up to bn minus 1. So this is how you will get bn minus 1 and b0, which is required in this condition. So we require bn minus 1 to be greater than b0. So we require this bn minus 1, magnitude of this, to be greater than the magnitude of b0. Okay, so once you construct this, the remaining things are the same. So something like the fifth row becomes c of n minus 2. So in order to get c of n minus 2, we need to get the determinant of these two along with the last two. So this forms c of n minus 2. Now in order to get c of n minus 3, first two columns along with the second last two elements. So it becomes c of n minus 3. And hence it continues up till c0. Now what will be the sixth row? Sixth row will be the same, c0, just the reverse of fifth one, c0, c1, etc. up to cn minus 2. And we require, and the condition is that we require c of n minus 2 to be greater than c0. So we require this term c of n minus 2 to be greater than c0. So this will continue till, so it is important, till we have 3, so this will keep on reducing, right? So here you have n elements, and in the second iteration we have n minus 1 columns. Here you have n minus 2 columns. So this need to continue till there are three columns. Okay, so till we have three columns, we need not go beyond that. Okay, so that is the construction of jury's table. So this is how you will find, you will check the stability using jury stability test. You check this condition, you check this condition, the third condition and fourth condition by constructing jury's table. So I'm not, yeah, maybe I'll quickly give an example. You can check it by yourself. The characteristic equation is given by P of Z equal to Z raised to 4 minus 1.2 Z cube plus 0.07 Z square plus 0.3 Z minus 0.08. So the characteristic equation is given like this, and this is being equated to 0. So if you need to check the stability by jury stability, you need to check the first condition is that whether A4, the magnitude of A4 is less than A0. Okay, so here what is A4? A4 is actually 0.08, which is in fact less than A0, which is 1. So this is A4 and the magnitude of Z raised to 4 is A0, which is 1. So the first condition is satisfied. The second condition is you need to find P of 1, and you'll see that P of 1 is 0.09, which is greater than 1. So the second condition is satisfied. Third condition requires that P of minus 1, so you'll get P of minus 1 as 1.89. Sorry, this is greater than 0. Sorry, it also need to be greater than 0 for since n is even. Here n is 4, so n is even, so we require P of minus 1 to be greater than 0. That is also satisfied. Now for the fourth condition, we need to construct the jury's table. So I'll quickly draw the jury's table in this case. So we have rows here 1, 2, 3, 4, 5, 6, and column wise we have Z raised to 0, Z raised to 1, Z square, Z cube, Z raised to 4, right? And the coefficients, I'll write the coefficients quickly. So the coefficients are minus 0.08, 0.3, coefficient of Z square is 0.07, coefficient of Z cube is minus 1.2, coefficient of Z raised to 4 is 1. So this is first row. The second row is just the reverse, so it is 1, minus 1.2, 0.07, 0.3, minus 0.08. So that is the first two rows. Now how to get the third row? So in order to get the third row, first element, you need to take the determinant of this first column and the last column. So it is 0.8 square minus 1 square, which turns out to be, second row first element becomes minus 0.9936. Okay, so that is the first element in the third row. What will be the second element? Second element is this first column, determinant of first column and the second last column. Okay, minus 0.08 into 0.3 minus 1 into minus 1.2, which turns out to be 1.176. Similarly, the third element will be minus 0.0756. The fourth one will be minus 0.204. The fourth row is just the reverse, that is minus 0.204, minus 0.0756, 1.176, minus 0.9936. So I'll quickly write the fifth and sixth as well. So fifth row is obtained by the determinant of this first column along with the last column. Okay, so it forms the the fifth row first element will be 0.946. Second row is obtained by this two elements and the second last two elements. So it forms minus 1.184. Third element is 0.315. The sixth row is as the reverse, 0.315 minus 1.184, 0.946. And we need to stop till we have three columns. So we don't need to go beyond this. And what we need to check is whether the magnitude of this value is greater than this. Yes, it is the case. The magnitude of this is greater than this. So 0.9 is greater than 0.2. And similarly, magnitude of this need to be greater than this. Here you can see that the magnitude of this is greater than this. And hence the fourth condition B, yeah, so you need to complete this. Maybe B3 is greater than B0. So you need to write the value. Similarly, C2 is greater than C0. Since these conditions are satisfied, the system is stable. If any of these conditions are not satisfied, then the system is unstable. So that is about jury stability test. Now I'll quickly mention about the third method, which is bilinear transformation with the Routh stability condition. So bilinear transformation with Routh's stability criteria. So it is a pretty straightforward way. So the method is there are two steps. So I'll write the steps. So step number one is you are provided with the difference equation P of Z equal to 0. So wherever Z is there, you replace it by the bilinear transformation, which is Z equal to W plus 1 divided by W minus 1. Okay, so this is actually the bilinear transformation. So once you transform it using this transformation, you will get a new polynomial, which is maybe given by Q of W. So Q of W equal to 0. So the given characteristic equation was P of Z equal to 0. Now using this bilinear transformation, we have transformed it into a new characteristic equation, which is Q of W equal to 0. So the significance of this W is it is something similar to the S plane, and hence for stability we require the roots of this characteristic equation to be on the left side of S plane. Okay, so in order to check that, we can use step 2. As a step 2, we can use Routh's array to check the stability. So this Routh's array is there in continuous time case as well. And so in constructing a Routh's array, if there is the number of sign changes of the first column, so I'll demonstrate with an example. So I'll tell quickly. The number of sign changes in the first column corresponds to number of poles or number of roots which are on the right side of W plane. Okay, so that is how we will check the stability in the case of bilinear transformation with Routh stability criteria. So I'll quickly write a problem. So if you are given with the characteristic equation P of Z equal to Z cube minus 1.3 Z square minus 0.08 Z plus 0.24. Suppose this is the characteristic equation, this is being equated to 0. So the first step is we need to transform it into W domain by using bilinear transformation. So use the transformation is equal to w plus 1 divided by w minus 1. So we'll write q of w as q of w equal to w plus 1 divided by w minus 1 the whole cube minus 1.3 into w plus 1 divided by w minus 1 the whole square minus 0.08 w plus 1 divided by w minus 1 plus 0.24 equal to 0. And so we can expand and we can find the polynomial. So this is equal to 0.14 w cube minus 1.06 w square minus 5.1 w minus 1.98 equal to 0. So this is the new characteristic equation in the w domain. Now you need to construct the roots array. So in order to construct roots array, we need to write like this. So w cube, w square, w raised to 1, w raised to 0. So this is the first column, and we need to fill the first two rows. So the elements are the coefficient of w cube we need to write first, which is 0.14. The coefficient of w square, it is minus 1.06. So remaining things we need to write like this. So first we return the coefficient of w cube, then w square, then the coefficient of w is written alongside with the coefficient of w cube. So it is minus 5.1 minus 1.98. So this is first two rows of roots array. Now how to get the third row element? So how to get this element? So this is obtained by doing this operation. Okay, so you multiply this into this. So you multiply minus 1.06 into minus 5.1 multiplied by these two divided by minus 1.6. So if you have gone through the roots array in continuous time case, you will be familiar with this, but I'll just write for simplicity of understanding. So this element is actually minus 1.06 into this into minus 5.1 minus these two elements. So it is minus 0.14 into minus 1.98 the whole divided by minus 1.06. Okay, so this will get you the third row first element, which will turn out to be minus this turns out to be minus 5.36. Okay, so there is no element here because so you cannot multiply. There is no element there. So here you have 0, here you have 0, so it becomes 0. So this value becomes 0. Now how to get the value of fourth row first column? So this is actually obtained by multiplying this into this minus this into this divided by this, which turns out to be minus 1.98. This is minus 1.98. Okay, so this is nothing but minus 5.36 into minus 1.98 divided by minus 5.36, which is minus 1.98. Okay, so this is how you will construct the roots array. And if you can see that the number of sign changes. So what is the number of sign changes? Here it is positive, it becomes negative, then it remains negative. So the number of sign changes is equal to the number of roots which are on the right side of W plane. Okay, so here there is one sign change. So there is one sign change. One sign change means one root on right hand side of W plane, which means that there is pole one pole outside unit circle in Z plane, and hence the system is unstable. Okay, so this is the method by which you will check whether the given system characteristic equation is stable or unstable by using bilinear transformation along with a Routh's array. So please try out the previous question that we have done. So this question with bilinear transformation and Routh's array. So here we have obtained as stable. So you check this question with bilinear transformation and Routh's array. Okay, so in this video we have discussed the stability analysis. In particular, we have discussed the absolute stability. We haven't considered the relative stability concept. We have considered the absolute stability, whether it is stable or not. Okay, thank you.